Welcome to Asking the Right Questions First, a design-oriented primer to robotics. This video will explore the fundamental design questions that precede the technical details of robot mechanics. Traditional robotics courses often start with links, joints, and equations, leaving students unsure why certain robot structures dominate. Here, we slow things down to ask why robots are built the way they are, giving meaning to the rigor. Robotics is the act of making structured engineering decisions under constraints. Every robot embodies answers to design questions. Unexamined design choices often lead to inefficient, unsafe, or overly complex systems, making it crucial to consciously address these questions. Question 1. Will a robot solve the problem? Robots are justified when tasks demand repeatability, precision, endurance, or operation in hazardous environments. If a task is simple and infrequent, robotics might add unnecessary complexity. Question 2. How well must the robot perform? Performance metrics like accuracy, speed, and stiffness directly shape the mechanical structure and control strategy. High performance creates trade-offs, not free improvements. Question 3. What is the operating environment? The environment determines material choices, sealing, sensing, and failure tolerance. Ignoring the environment leads to fragile designs, especially in hazardous or constrained settings. Question 4. Fixed or mobile? Fixed base manipulators are common in early education because they are kinematically tractable. Mobile robots introduce challenges like localization and navigation, reflecting a key architectural decision. Question 5. Size, scale, and inertia. A robot's physical scale affects acceleration limits, energy consumption, and structural stress. Small robots move quickly, while large robots require careful dynamic and safety considerations. Question 6. Moving parts and degrees of freedom. Degrees of freedom answer how many independent motions are required for the task. Increasing them adds complexity and flexibility. Redundancy is a conscious design choice with consequences. Question 7. Can we write governing equations? Robots must be mathematically describable for prediction and design validation. If we cannot write equations, we cannot reliably predict behavior. Equations are contracts between design and reality. Question 8. Can we simulate the robot? Simulation allows us to test ideas, expose failure modes, and assess parameter sensitivity without damaging hardware. Intuition alone is insufficient. Simulation is critical in serious robotic design. Question 9. How complex should the robot be? Complexity increases cost, maintenance, and failure probability. A simple, reliable robot is often superior to a complex one. Engineering maturity means choosing the minimum required complexity. Question 10. Control, autonomy, and task structure. Autonomy exists on a spectrum, from teleoperated to fully adaptive systems. Repetitive tasks demand reliability, while diverse tasks require flexibility. These choices shape the control architecture. Question 11. Interaction, safety, and humans. As robots share spaces with people, safety, compliance, predictability, and trust become design requirements. Robotics involves ethical and societal considerations, influencing acceptance and responsibility. Question 12. Materials and manufacturing. Material choice affects stiffness, weight, durability, and cost. Manufacturing processes constrain geometry and tolerances. Ignoring manufacturability leads to designs that exist only on paper. Question 13. Sensing, power, and communication. Robots perceive via sensors, act through power, and coordinate using communication. These decisions define the robot's operational envelope, reinforcing that mechanical structure alone is insufficient. Learning robotics is about cultivating a way of thinking, not memorizing robot types. Every technical concept you study is an answer to one of these design questions. Understanding the questions first will ensure the mathematics make sense.